Hello, my name is Elrid, and today we will be going over my findings in Lab 5, Faraday's Law. In this lab, I hope to develop an understanding of Faraday's Law and show how the EMF produced in a conductive tube by the motion of a magnetic dipole creates an induced current that can create a magnetic force on the magnetic dipole. I do this by dropping a bar magnet through a roll of aluminum foil and measuring the time it takes for the magnet to exit the tube, which is longer than it would normally take for a magnet to fall through a non-conductive tube of this length. I then created a computational model of this experiment by creating magnet and tube objects in VPython, where the tube is approximated by a series of rings. Some useful equations when doing this lab include Faraday's law, from which we can derive an expression for the EMF on the rings, where y is the vertical distance between the magnet and the ring, and rho is the radius of the tube. We also will use the expression for the magnetic field of a magnetic dipole from Lab 3 and Ohm's law from Lab 4 to determine the magnetic force on the loop. This is combined with the gravitational force on the bar magnet to determine the net force, which is then used with the momentum principle to update velocity and position. Looking at my experiment, the length of the roll was about 30 centimeters, with an inner radius of about 1.5 centimeters and a thickness of 0.5 centimeters, and the magnet took an average of 0.972 seconds to fall through the roll of foil. Looking at the slow motion of the magnet falling through, we see that it exits the tube at an angle, and I observed that as the magnet falls, it is not falling vertically through the tube. Looking at my code, I start by defining my stationary bar magnet with the mass of the magnet I used in my experiment and my mu value from Lab 3, as well as my roll of foil with the measurements from the previous slide. Other parts of the code split the tube into rings, which we will perform our calculations on. I will then define functions for the magnetic field of a dipole and d flux dt based on the previously stated equations. We then call the d flux dt function to then determine the current using Ohm's law. We also determine the gravitational force on the magnet as well as an r vector between the ring and the bar. Here, I call my magnetic field function using my mu and r vector, determine sine theta between mu hat and b hat using the cross product, and use these along with the current I found to find the magnetic force. This, added to the gravitational force, gives a net force. Finally, I will use the net force and the momentum principle to update the velocity and position of the bar, after which the code loops until the bar leaves the tube. Parts of the code also record and plot the velocity of the magnet with respect to time, and we see that at the beginning and the end of the code running, the velocity is at its greatest when the magnet is in free fall, not being influenced by the force from the tube. We can also see that the magnet is at constant velocity in the encircled portion, where it is being influenced by the EMF of the tube. Comparing the time in the tube from my code to the average time recorded, the time in my experiment is smaller, which is likely caused by my magnet not falling evenly through my tube and therefore not evenly experiencing the effects of the magnetic force to slow the bar down. To end, if we reduce the resistivity of the conductive tube, we would increase the induced current produced in the tube and therefore increase the magnetic force on the bar. This would make the magnet fall much slower. The opposite would occur if we were to remove material from the tube, with the induced current getting weaker, weakening the magnetic force and allowing the magnet to fall quicker. Thank you for watching.